Alright guys, we're going to be talking about oblique asymptotes today. And a couple things you need to know before we get started. Oblique asymptotes are also called slant asymptotes, okay? And they only occur when the degree of the numerator is 1 degree higher than the degree of the denominator. So remember when we talked about horizontal asymptotes when m equaled n, or when m was less than n, we had a horizontal asymptote. However, if we have m is greater than n by 1, we're going to have what's called this slant asymptote, or oblique asymptote. Okay, we can find slant asymptotes by using polynomial division. Okay, and remember there's two ways we can use polynomial division, long or synthetic division. And it's important to realize that these oblique asymptotes are always lines. The other thing to realize is that if you have an oblique asymptote, you are not going to have a horizontal asymptote. So oblique asymptotes are similar to vertical and horizontal, meaning a graph is going to get really, really close to these lines. So we're going to look at an example of polynomial division, and then we're going to look at how to find these oblique asymptotes. Okay, so in problem number 1, we're going to divide 2x squared minus 3x plus 3 by x minus 2. And what I've done here is set up two ways to do this. I've set up long division and I've set up synthetic division. Remember, we can only use synthetic division if we have a linear factor. Okay, so it's really important to realize. So let's look what happens when we divide using long division. And we follow our rules for regular division. We think, what times x can give us 2x squared? Well, 2x times x gives me 2x squared. So I write that in, and I multiply 2x times the x and 2x times the minus 2. And that's what I get right here, that product, 2x squared minus 4x. Again, with long division, we have to subtract off that whole term. And really what we have left is the remainder. Okay, so now we look. Does x go into x? Yes, it does. X goes into itself one time. So you take that 1 and multiply by x, and you multiply that 1 by minus 2. And we get x minus 2. And again, you have to subtract off that entire term. So there's our remainder. The value here on x would be 0. It is less than the divisor, so we are done. So the answer would be 2x plus 1 plus 5 over x minus 2. That's the remainder right here. Okay? Now, synthetic division, we have x minus 2. We put the 0 here. Okay, so whatever would make this 0, that's what goes here. So we put the coefficients of each variable here, 2, -3, -3, and we go from largest to smallest, and we never skip a power. So if a power is missing, we add that 0. So we have 2, we drop the 2 down. 2 times 2 is 4. Add -3 and 4, you get 1. So we have 2 times 1, which is 2. And you add 3 and 2 together, you get 5. Notice how we have remainders here of 5. So the answer is the same. It better be, okay, because we're just using two different methods of division. So what's great about finding oblique asymptotes is if you use polynomial division, you've already found it. The oblique asymptote or slant asymptote is just the quotient right here. You just actually ignore the remainder. So right up here, 2x plus 1, that would be the oblique asymptote. And we know that one would exist because the numerator has a power 1 degree higher than the denominator. So this would have an oblique asymptote, and that would be 2x plus 1. Now, in example 2, we're actually going to determine the oblique asymptote of y equals 6x squared plus 14x plus 7 over 2x plus 3. Okay, so what we're going to do here, this is still linear, okay, and we could find the 0, but it'll be a little more tricky because you'd have a fraction, so I'm actually just going to use long division here. So I put my divisor out front, and I think, what does 2x go into 6x squared? And it does, 3x times. So that 3x gets multiplied to both these terms. 3x times 2x is 6x squared. 3x times 3 is 9x. I line up appropriate powers, like terms, okay, and I subtract off that whole blue amount. And 5x plus 7, that's your remainder so far. Does 2x go into 5x? It does 2.5 times. So we're going to have 5 halves here. So we have 5 halves times 2x is 5x. And I made that in red just to show you that these two need to be equal and cancel out. So 2x does go into 5x, it's just not an even number of times. So it's 2.5. So 5 halves times 2x is 5x. 5 halves times 3 is 7.5. So I just converted that to decimal. It's really 15 halves, or 7.5. So I subtract out both those terms, and I'm left with -1/2. This power on x would be 0. It is less than the divisor, so I know I'm done. So I know that 3x plus 5 halves is my oblique asymptote. So the line y equals 3x plus 2.5. That's my oblique or slant asymptote. Remember, these oblique or slant asymptotes are lines, so it's going to be in that form y equals, and it's usually going to be y equals mx plus b form, slope-intercept form. Okay, so that's my answer. Remember, when you talk about oblique asymptotes, ignore the remainder. Okay, ignore the remainder. Use division, ignore the remainder. Alright, so I wanted to show you another example here and use synthetic division. So determine the slant asymptote of y equals 2x squared minus 3x plus 3 over x minus 2. Okay, so in this case the divisor is linear, so let's use synthetic division. It's x minus 2, so the number out there is going to be 2. That would make the denominator 0. My leading coefficients come down, okay, and I have dropped down the 2, so you have 2 times 2 is 4. Negative 3 plus 4 is 1, okay, and so I have 2 times 1 is 2, 3 plus 2 is 5. So again, different equation, different factor, but again, this oblique asymptote is 2x plus 1. So we've seen a couple where we have 2x plus 1. Just be careful, don't always think that all the oblique asymptotes are going to be 2x plus 1. They're not going to be. Okay. So what do graphs of rational functions look like with oblique asymptotes? Well, let's look at an example. So in problem number 4, I just asked you to graph something, this rational function 2x squared over x plus 1. So we're going to handle this like any other rational function. You're first going to find the asymptotes if they exist, and then you're going to draw those in and use a table of values to help you graph the rest of the function. So the vertical asymptote here, it does exist. It's -1. Okay, it's not removable because these are not common factors, so we know it's a vertical asymptote. So at -1, I draw a red line vertically. Number 2, I put on here, remember, there's no horizontal asymptote, okay, because the power on the numerator is greater than the denominator, so there isn't one. And since the power on the numerator is greater than the power on the denominator by 1, there's actually an oblique asymptote. Okay, so that's things you got to think about. Okay, since m is greater than n, there is no horizontal asymptote, but since the power on m plus 1 equals n, it's greater than n, we have an oblique asymptote. It's 1 greater than n. So we know there's an oblique asymptote, and I mentioned that. So I just quickly use synthetic division to find that line. And I put -1, okay, because this is my linear factor. Okay, so -1 goes on the outside, 2, and notice in red I have 0, 0. I only have 2x squared. I don't have x and I don't have the constant, but you still have to account for those. So the 2 drops down. -1 times 2 is -2. 0 plus -2 is -2. -1 times -2 is 2, and the remainder is 2. So my line is y equals 2x minus 2. So I plot that linear equation. My y-intercept is -2, up 2 over 1, so then there is my oblique asymptote. Now, how do I graph this? Well, you plug in values. You have to pick points, again, to the right of the vertical asymptote and points to the left. For example, if I plug 0 in for x, 0 over 1 is 0. Okay? If I plug 1 in for x, 2 times 1 squared is 2 over 2, which is 1. So when you use an x value of 1, you get 1 for y. So there's that point right there, 1, 1. So I kind of have enough information to generally sketch my graph. So I have these 2 points, and I just follow my asymptotes. So there's one portion of this graph. I got to get the other portion. So what I do is I plug -2 and -3 in. When I plug -2 in, I get 8 over -1, which is -8, so -2 all the way down to -8. When I plug -3 in, okay, I get 18 over -2, which is -9, all the way down here. Got 2 points, and I follow my asymptotes so I can generally sketch my graph. A couple things I want you to be very careful of when you're dealing with asymptotes and trying to find oblique asymptotes. And I didn't put an example on here, but if you have 2 factors in the denominator, you need to multiply those out first before you divide. Okay, that's number 1. Okay, number 2, if you have the numerator and it's just factors, okay, multiply those out too. Okay, that's very important that you have polynomials in standard form in the numerator and denominator before you start adding, subtracting, or excuse me, before you start polynomial division. You need to be aware of that. Okay, so that's oblique or slant asymptotes. If you have any questions or comments, you can email me or put a comment below, and I'll try to answer as quick as I can. We'll see you next time.